Oh, you were close. Okay, guys, so the topic, your notes today is acids, bases, and pH. What you're going to find out is we're actually going to build on the stuff that you learned last time while doing the lab. You probably picked up on this given the fact that I didn't actually grade your labs, but I just put the blue bug stamp on your labs when you brought them to me and they were correct. Guys, the whole purpose of that lab was not to make sure you understand something, because we grade those more carefully. Guys, the purpose of that lab was to introduce you to concepts that we're now going to follow up on and flesh out. So guys, today what we're going to do is we're going to talk about acids, bases, and pH. And so let me sort of set the stage for you a little bit, and then we'll get going. The date today is the 17th, St. Patrick's Day, if you're dating your notes. So I'm trying to make a corned beef for the first time in my life for St. Patrick's Day. I've already put Papa John's on speed dial on my phone, so if it goes horribly wrong, we're just going to order pizza. But we'll see. Well, we'll see. I've got this big chunk of beef resting in my refrigerator, soaking in about 1.5 gallons of salt water. So I don't know. It could be horrible. All right. So guys, first 2 slides, don't write anything down. Here's where we're at. So guys, this is what you should at least have some idea about given what we did last time in lab. Again, not a deep understanding, but from that silly lab that we did where you're doing that serial dilution and squirting indicator into stuff. Guys, these are the thoughts that you should at least be a little familiar with. First of all, this, acids have lots of hydrogen ions. That okay? Okay, so guys, if acids have lots of hydrogen ions, what do bases have? Lots of hydroxide ions. So remember, acids have got lots of H, bases have got a lot of OH. So what happens when you react an acid and a base together? What do you get? You get water. The hydrogen from the acid, the OH from the base. When those things come together, they make water. So water has equal amounts of hydrogen and hydroxide. That's H2O. So guys, which one is it? Is water an acid or is water a base? It's both. So guys, if you add an acid to water, water functions as a base. If you add a base to water, water functions as an acid. And we're going to talk more about that in just a minute. So then guys, the next thing we talked about was pH. And you guys understand that pH is a scale that allows us to measure the strengths of acids and bases, but it is not an arithmetic scale. It doesn't go up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What kind of mathematical scale is pH? Logarithmic, and the idea, guys, is that it moves by powers of 10. So guys, let's talk about this. Why are logarithmic scales useful to us? What does it allow us to do? Well, guys, imagine if I wanted to count arithmetically to 1,000,000. Okay, so say I just want to count to 1,000,000, and I'm going to do this arithmetically. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Where am I going to end up by the time I hit 1,000,000? Like Idaho, right? But now, guys, imagine that I want to account to 1,000,000 and I'm going to do it logarithmically. Then it just goes 10, 100, 1,000, 10,000, 100,000, million, and I'm there. Because that's the reason logarithms are helpful to us, is because it allows us to count really big and really small numbers really easily, because it doesn't progress by powers of 1, it progresses by powers of 10. If you think of logarithms that way, I think you'll find it helpful. So guys, does this all jive with you? Is this where we're all at? We all okay with these ideas? You're good? All right. So guys, with that said then, again, don't write this down. What are we going to do today? Well, guys, today what we're going to do is we're going to answer some questions. So question number 1 is, what is an acid and what is a base? You already understand that acids give away hydrogens, bases give away OHs, but it's not quite that simple. So we're going to talk about 2 different definitions for acids and bases. When you get to college, typically your sophomore year, you'll find out that there's a 3rd definition to acids and bases, but we don't worry about it here at Orem High or in high school. Then guys, the second question we're going to ask is this. When acids and bases react together, what do? And then we're going to follow up with that with what do acids form when they react together. And we already understand that they form water sometimes, and we're going to dig into that a little more deeply. And then guys, finally we're going to answer this question. Why is it that stronger acids have lower pHs? Remember we learned last time that the pH scale goes from 1 to 14, and the acids are down, the strong acids are down near 1, and then they get weaker as we move up towards 7. And what has a pH of 7? Do you remember? Distilled water. And so guys, we're going to talk about why is it that the lower the number, the stronger the acid. And then you're going to grab your calculators. That's my phone. You're going to grab your calculators and you're going to figure out how to calculate pH, and then we're done for the day. You guys ready to go? Okay. So guys, let's do this to get started. Again, you're not going to write any of this down, but here's the idea. So guys, when we talk about acids, chances are good you could come up with examples of acids. So what do you got? Battery acid. Do you know what kind of acid battery acid is? It's actually sulfuric acid, and I'll throw that up in a minute. Guys, what else are acids? Hydrochloric acid. Guys, where do you find hydrochloric acid besides in my lab? Do you guys not know? Your tummy. Guys, your stomach is a bag of hydrochloric acid. Inside your stomach is hydrochloric acid that's actually surprisingly acidic. Its pH is somewhere between 2 and 3. So guys, if your stomach is a bag of acid, why is your stomach not like burning itself? Melting itself. And so guys, so inside your stomach, there's a lining that protects your stomach from this really strong hydrochloric acid. But guys, what happens if that lining fails? You digest your own stomach. And what do we call those? Ulcers. Guys, that's what an ulcer is. By the way, that lining that's inside your stomach is literally boogers. It's mucus. Same stuff that flows out of your schnozzle when you get a cold. Guys, your stomach is lined with mucus, and when you get a hole in that mucus lining, you start to digest your own stomach, and it's called an ulcer. Yeah. Absolutely. Well, and it's even worse because you know how it is when you throw up, or it sounds worse, I mean weird, but you know how sometimes you like hiccup or frankly you'll burp and it burns a little bit? The reason is because that acid is sloshing up into your esophagus, and your esophagus is not lined with mucus and it burns. They call it heartburn. Yeah, but yeah, worst case is you throw up, and if there's no food, you know, it burns your nose and your throat. That's that acid, and that's the way your stomach would feel if it weren't for that mucus lining. Guys, what other things are acids? Good, which you find in grapefruits and oranges and lemons and limes. So citric acid, you guys got anything else? What else? What are other things in your world that you know are acids? How about this one? Vinegar. Guys, the vinegar that you put on your salads, that's actually called acetic acid, and that's an acid as well. So anyway, we didn't do too bad. So let me give you the examples that I came up with. We're going to start with your example. Guys, battery acid. Inside your car is that plastic container full of lead sheets, and those lead sheets are soaking in sulfuric acid, H2SO4. And so guys, that's actually what stores the charge in your car. Another example of an acid, and you guys came up with this one too, is stomach acid, which is hydrochloric acid. Same stuff we use in lab. But then guys, what about this one? I think some of you have probably heard about this. One of my favorite female cyclists, Lizzie Armistead, when you push so hard that your body can no longer keep up and can't get oxygen to your muscles quickly enough, your metabolic cycle changes to an anaerobic cycle, and what builds up in your muscles? Lactic acid, which is actually C3H6O3. And then guys, finally, the last one, which you also came up with, is citric acid. So guys, here's the question. What do all these have in common? Hydrogen. Doesn't that make sense given what you understood? Guys, that in order for a substance to be an acid, it's got to contain hydrogen, because that's what acids do, give away hydrogen. Does that make sense? Okay, so you ready for the room to go silent? Let's have the same conversation about bases. Really? Do you know a base? Good. Bleach is actually a base. I didn't I don't think I put it in my pictures. I should add it because that's cool that you came up. No, bleach is definitely a base. Yeah. Chlorine, no, it's actually not. What else? You guys know any? Oh, good. Wow, you guys are doing better than most. Guys, mostly cleaning supplies. Guys, ammonia, so let's talk about it. All soaps are bases. Did you guys know that? All soaps are bases, including bleach and ammonia. Other things that are bases. Good. Yeah. Oh, you guys should have got that one, right? Did I tell you about that in the last lab we did? In the percent yield lab, that the sodium bicarbonate that we used as a base, that was actually just baking soda. Did I tell you guys that? It's disappointing, I know. When you call it sodium bicarbonate, it sounds like chemistry. When you call it baking soda, it sounds like your kitchen. But guys, that white powder that you had in that vial was just baking soda, and that is a base. So guys, what about these? This one is actually kind of interesting and yet obvious. Well, not this one. We already talked about all cleaners, including oven cleaner and all soaps and things like that. That's a base. And actually, oven cleaner is sodium hydroxide. What about this one? Rolaids. Yeah, so guys, what do you do? When do you take Rolaids? When this gets out of control. Right? When you've got so much HCl that your stomach is like, oh my gosh, just too full of acid, what you're going to do is you're going to fire back a base, and the base neutralizes the acid in your stomach. Turns out Rolaids is actually aluminum hydroxide. So Tums is actually calcium hydroxide. They use a different base. But Tums, Rolaids, the pink stuff, what's that called? Pepto is actually magnesium hydroxide. So yeah, but anyway, so you get the idea. So guys, what about this one? Ammonia. And actually, Trevor got that. Ammonia is a base as well. It's NH3. And then guys, the last one that I wanted to throw up is actually chalk. Did you know chalk is a base? And chalk is actually calcium carbonate. Yeah. That was my next question. So guys, let's talk. So if we look at these, remember what we understand about bases. Bases give away OH, right? So doesn't that make sense given these two? There's your sodium hydroxide, your aluminum hydroxide. Those are both bases because they contain hydroxide. But now, as Isabel's pointing out, guys, if you look at these bottom two, they are bases, but they don't contain hydroxide. But they still make hydroxide. And what that means, guys, is we've got some chemistry we need to talk about. So we can see that this makes sense, that these are bases because they contain OH. But how are these bases if they don't contain OH? And guys, that's what we're going to talk about next. So you ready to start writing some of this down? So here we go. So guys, in order to answer Isabel's question, how is it that this stuff is a base if it doesn't contain OH? Let's talk about the definitions for acids and bases. And guys, it goes like this. These definitions are actually named after the chemist that proposed them. So a guy named Arrhenius, I think this is like 1820s, 1830s. Arrhenius was studying acids and bases. The frightening part is Arrhenius didn't have universal indicator to figure out if something was acidic or basic. So guess how he figured out if something was an acid or a base? He tasted it. No, actually worse. He put it in his mouth. And guys, you already know that acids taste tart, right? Like citric acid, like vinegar. Acids taste tart. It turns out bases feel slimy and taste bitter. And that's how he was actually studying these, was by tasting them. And amazingly, he didn't die. But guys, along the way, this is what he proposed. He said that acids release hydrogen ions. And then we could add into water, but that's okay. So guys, acids release hydrogen ions. And then he proposed that bases release hydroxide ions. Bless you. So guys, when this happens, when an acid releases a hydrogen and when a base releases an OH, we've already talked about it, what do the H and the OH make? Water. So guys, this is what the general reaction looks like. So you take an acid, you take a base. The acid releases hydrogen, the base releases OH, the H and the OH make water, and then the things that are left over come together and they make salt. Remember, salt is not just NaCl, there's lots of different salts. But guys, this is the general form of a Arrhenius acid-base reaction. So guys, let's take a stab at this. Pick your favorite acid. What is it? Citric. Oh, I don't know the formula for that. Pick. Okay, so let's do stomach acid. Whoa! Hold on, I gotta quit out of this because this freaks out. All right, get rid of that. Go here. Get out of that. Go here. Quit this. This is such a pain. Restart this. Go here, and then go here, and then go like this, and then like this. And then I should be able to write, and sure enough, and here we go. Okay, so guys, we're gonna use HCl as our acid. Now guys, pick your favorite base, but let's not do sodium hydroxide. It's gotta be one that contains OH. How about, let's just do the reaction that happens in your stomach. How about that? So guys, let's take Rolaids. So guys, Rolaids is aluminum hydroxide. So what is this going to form? Well, as this reaction takes place, we know that the acid is going to release hydrogen and the base is going to release OH. And what does that make? That makes water. Because remember guys, water we can think of as being HOH. And then guys, what's our other product? When we take the H away from the acid and when we take the OH away from the base, what's left? Aluminum and chlorine, but aluminum's +3, chlorine's -1. So this is AlCl3, and this isn't balanced. Well, let's balance it. Done. No, it's done. But guys, the bottom line is this. That is the reaction that goes on in your stomach if you fire back a Rolaids. So the aluminum hydroxide reacts with the hydrochloric acid in your stomach. That makes water. By the way, what's the pH of water? 7. So it's neutralizing the acid in your stomach. And then it also makes aluminum chloride salt. And that's how Rolaids works. You get the idea? Okay, so guys, given this definition and given the idea that Arrhenius understood that bases give away OH, this makes great sense. But now we run into a problem, and the problem Isabel already pointed out to us. Guys, what about these dudes? What about them? They don't contain OH. So how can these things be bases if they don't contain OH? Well, guys, it turns out this was a problem that disturbed chemists all through the 1800s until along came two dudes named Bronsted and Lowry. And so Bronsted and Lowry were trying to figure out the very same question that Isabel pointed out. How is it that things can be bases if they don't contain OH? They knew that ammonia, they knew that chalk, they knew that bleach, they knew that those things were bases, but they couldn't figure out why, because they didn't contain OH. Well, guys, it turns out Bronsted Lowry figured it out. And it goes like this. So in the Bronsted Lowry definition, acids are proton donors. They give away protons. But now, guys, here's what I want you to do. Compare that definition to the Arrhenius definition. What did Arrhenius say acids do? Give away hydrogen ions. What does Bronsted Lowry say acids do? Give away protons. Guys, guess what? They're the same. You may want to draw a little line between those two definitions and write down they're the same. Because, guys, it turns out hydrogen ions are protons. Check this out. You can write it down if you want. So, guys, let me show you what I'm talking about. So this is a hydrogen atom, right? 1 proton, no neutrons, 1 electron. Remember when we used to do that? Like back in like forever ago, like October? But guys, this is a hydrogen atom. 1 proton, no neutrons, 1 electron. Now guys, here's the trick. What Arrhenius said was this. Arrhenius said that acids give away hydrogen ions. So what do we have to do to this atom to make it into a hydrogen ion? What do we take away? An electron. And when the electron goes away to make it a hydrogen ion, what do we have? A proton. That's all that's left. So guys, hydrogen ions and protons are the same thing. Does that make sense? Okay, so guys, now we understand that the Arrhenius and Bronsted Lowry definitions for acids are the same. Here's where it gets different. Check this out. This is what Arrhenius said about bases. Arrhenius said bases are proton acceptors. So guys, that was the difference. Because look at how this changes things. Guys, go up and look at the Arrhenius definition. What did Arrhenius say a base does? Gives away OHs. So guys, in the Arrhenius definition, a base has to contain OH in order to function as a base. But guys, in the Bronsted Lowry definition, all a base has to do is take in protons. So now bases don't have to contain OH in order to be a base. All they have to do is take in protons, and these can be a base. But guys, check this out. Write this down with me, because this is really pretty brilliant. Because here's the idea. Take NH3 and include this in your notes. I'm going to write this into my notes. Frankly, I've never shared this with a class before, but I'm realizing you guys are bright enough to figure this out. So how does this work? So guys, take for example NH3, which is ammonia. And we found out in that picture that ammonia is a base, and now we're going, wait, how is ammonia a base if it doesn't contain OH? Well guys, here's the trick. You take ammonia and dissolve it in water. Now guys, it may be helpful to do this. Remember that we can think of water as HOH. Do you get it? Do you see what it's going to do? Guys, what does Bronsted Lowry say bases do? They take in hydrogens. So guys, this base, NH3, is going to steal a hydrogen from water. And when it does, it actually forms NH4 with a positive charge. And then guys, what's left over? OH. There is your hydroxide. So guys, it turns out that in the Bronsted Lowry sense, bases don't have to contain OH because they can make OH by taking water and stealing a proton, a hydrogen, and when the base steals a proton from water, the thing that's left over is OH, and so it makes OH rather than containing OH, but because it makes OH, it makes it a base. You get the idea? So guys, that totally unpacked the whole problem that Isabel noticed, because remember when we ran into this problem, we realized that these guys down here shouldn't be bases because they don't contain OH. Well, it turns out Bronsted Lowry explained it, because the reason these function as bases is because they steal a hydrogen from water, and when they do, they make OH rather than containing OH. Pretty good, right? That's good chemistry. All right, so guys, with that said then, let's flesh out this idea of Bronsted Lowry acids and bases. So we've got this idea, but now we need to talk about the general reaction, and we're going to talk about some new terms. So guys, the general reaction goes like this. An acid reacts with the base, and it makes what is called a conjugate acid and a conjugate base. So write it down and then we'll talk about it. A I'm making notes to myself because I really like the way that went. Did that make sense? I've never taught this stuff that way. So you're going, then how did you do it? Different. And not as well. That was actually, that was really clear how it makes OH? Frankly, I've been scared to death to share that with general chemistry students. I've always waited until AP, but that just sort of happened, and that was beautiful. All right, so guys, now we've got some new terms we need to talk about. This idea of conjugate or conjugate. Conjugate's a verb, conjugate's a noun, doesn't matter. So guys, what does it mean? French, Spanish, you guys taking foreign languages? All I remember, I took Spanish, and I remember, did they still talk about shoe verbs? No? Yes. Boot verb, yeah, I still don't know what that means. I just remember I was supposed to know. But guys, I know that in Spanish, and I think in French as well, you conjugate verbs, right? What does it mean to conjugate something? To change its good, to change its form, to change it into something new. Well, guys, that's what conjugate means. It means to take something and turn it into something new. So if you want to, if this is helpful, you could maybe above the word conjugate, and I'm going to do this, you could actually write the word new. Because that's what we're actually doing. We're taking an acid and we're taking a base and we're turning it into a new acid and a new base. So guys, I'm going to give you some explanation on this, and for some of you are going to go, wait, that doesn't quite make sense. But when we start playing with it, I know that it will. So let me define this for you. So you're going to want to get this in your notes. So guys, conjugate acid. What is a conjugate acid? Well guys, a conjugate acid is the acid that is formed when a base gains a proton. So you may think about it this way. Base plus proton equals conjugate acid. But guys, notice the charges. This is important. The conjugate acid's charge goes up. Because the proton is positive, protons are positive, because the proton is positive, the charge of the acid goes up. And then guys, conjugate bases are formed when an acid releases a proton. I know I'm going fast, I'll stop in a minute. Conjugate bases are formed when an acid releases a proton. So you could say acid minus proton is the conjugate base. And notice that the charge goes down by 1. I'm going to change that. The charge, we'll just say, goes up by 1. Oh, that's an I. And the charge, that'll be enough to remember, goes down, good heavens, by 1. Okay, that'll work. Perfect. So guys, this is one of the things that you need to be able to do as a result of what we're doing today. It'll be on the test. It'll be on the SAGE test. Anyway, this is important. You've got to be able to look at an acid-base reaction and figure out which is the acid, which is the base, which is the conjugate acid, and which is the conjugate base. Now understand, that's all you've got to do this year is just be able to identify and label the parts. When you come back for AP next year, we spend weeks, months, talking about the chemistry of conjugates. Guys, this is a hugely important thing, but for this class, all you've got to be able to do is identify which is the acid, which is the base, which is the conjugate acid, and which is the conjugate base. So guys, did you get all this down? Not yet? I'll wait. How about now? How about now? Now? How about now? What did you say? Was it not important or was it offensive? guys okay? So let's do this. Guys, don't write down the 2 examples that I'm going to give you, but what you're going to see is as these examples come up, there's going to be some terms that we need to share, and those you will write down. But what I'll do is I'll step you through 2 examples of identifying acids, bases, and conjugates. You will write down the additional terms that are going to come up, and then when we're done with that, I've got a whole nother slide full of practice problems. And if you say, yeah, maybe we'd like to try a few more, we will. If you as a group are going, no, I think we understand this, you'll see it in homework and you can make sure then. So, guys, this is what you got to be able to do. Again, just trust me on this. Don't write it down. So here we've got a reaction. It's H2SO4 and water, and the products are H3O plus and HSO4 minus. And guys, HSO4 minus is actually what's called bisulfate. So now we've got to figure out which is the acid, which is the base, and which are the conjugates. So guys, the acid and base are going to be on the left, and the conjugates are going to be on the right. So let's figure this out. So how do we figure out which is which? So guys, remind yourself, what do acids do? What do? Give away hydrogens. So guys, you go, and I'm going to do this wrong, but here's how you do it. You look at water and you ask yourself, did water give away a hydrogen? Well guys, if water lost a hydrogen, what does H2O turn into? Just HO or OH. So you're like, okay, so if water gives away a hydrogen, I'm just going to have an O and an H left. So now you look over here and you go, is there any HO over there? Well, no, so that must not have happened. So then you come over here and you go, oh, look, H2SO4. And if I take away a hydrogen from that, what's left? HSO4. So then you come over here and you go, oh, is there any HSO4? Oh my gosh, there it is. So because there's HSO4, that tells you that this is the acid. Does that make sense? Is that okay? So guys, as soon as you know which one is the acid, all the rest of this is super easy. Because if this is the acid, what does that make this? The base. So guys, that one is going to be the base. If one's the acid, the other's the base. Now the question is this: how do you figure out the conjugates? And guys, check this out. Here's all you got to do. To figure out the conjugates, go to the acid, cover up the hydrogen. So if you take the hydrogen off the acid, it turns into this. But the trick is the acid turns into the conjugate base. So it's the conjugate opposite. So if this is the acid, take away the hydrogen, and that makes that the conjugate base. Does that make sense? They switch roles. So if that's the conjugate base, what does it then make H3O? The conjugate acid. Guys, that's all you got to do. Okay? But along the way, we've got to talk about this critter, and you need to write this down. Guys, this actually, you know what? Oh, did I add 3 examples? Oh my gosh, guys, I added 3 examples. Never mind. Let's do this one as well then. So guys, acids, bases, and conjugates. Let me give you a second. You don't need to write this down, but try it in your head. Which one's giving away the hydrogen? That tells you the acid. As soon as you know the acid, you know the base. As soon as you know the acid, take away the hydrogen, that's the conjugate base, and then the other is the conjugate acid. So guys, let's try it. Is water giving away a hydrogen? Steve, track with me. Is water giving away oh gosh, I didn't mean to touch that. I got distracted. Let's try again. Oh, too many clicks. There, I know, right? So guys, is water giving away a hydrogen? No, this guy is, right? Because if you take away the hydrogen, that makes this. So that makes this the acid. And again, guys, once you know the acid, what's that? The base. And then to figure out the conjugates, go to the acid, take away the hydrogen, the other is the conjugate base, and then that's the conjugate acid. Does that make sense? Okay, now you need to write this down because this is important. Guys, see this stuff right here? This conjugate acid, H3O plus. Guys, that stuff is important. It is called hydronium ion. So guys, what is hydronium ion? Hydronium ion is H3O plus. Then the question is, why do we care about hydronium ion? Well guys, the answer is this. you'll notice that both of these are acids, and they are both being added to water. Well, guys, here's something we should talk about. In order for an acid to be an acid, it has to be in water. Acids don't function as acids until we dissolve them in water. It turns out that H2SO4 is a gas. You can buy it in a tank like helium. It turns out that CH3COOH is a powder. I've got a bunch of it over in lab. But guys, these gases and powders are not acids until you dissolve them in water. But guys, here's the trick. What do acids do? They give away hydrogens. Where do they go? They go to water. And so guys, anytime you add an acid to water, the acid adds a hydrogen to water and it turns into hydronium ion. So guys, hydronium ion is always formed when an acid is added to water. So guys, here's the trick. You're in lab. You're working with hydrochloric acid. You spill it on your arm and you're going, ow, hydrochloric acid is burning me. Owie, owie, owie. No, it's not. Guys, hydrochloric acid cannot burn you. The thing that's burning you is actually the hydronium ion that hydrochloric acid forms when it dissolves in water. So then you drink a glass of orange juice and you go, hey, that was kind of tart. It must be the citric acid. No, it's not. It's the hydronium ion that the citric acid makes when it dissolves in the water in the orange. See, guys, the acids themselves are not the things that we experience as tart or burning. It's actually the hydronium ion that they make that we experience as either being dangerous or tasty or whatever. So, guys, it's the hydronium ion that we think of as being acidic, but it makes sense because all acids form hydronium ion. Get the idea? So, guys, what's then the difference between hydrochloric acid that hurts and citric acid that's delicious? The amount of hydronium ion. Because it turns out that the only difference between the two is the amount of hydronium ion they make. Hydrochloric acid makes a lot and it's dangerous. Citric acid makes a little and it's tasty. But it's all hydronium ion. You okay with the idea? Okay, so what about this one? Guys, we've seen this one before. NH3, water, NH4, and OH. Where did we see this? Just a minute ago, right, when I explained to you why NH3 is a base. See, for years, I've been putting this in the notes, but I've never explained to students that this is why NH3 is a base. We just skipped right over it. Now you know. So guys, let's take that same reaction and figure out the acid, the base, and the conjugates. So you ready? Starting here. NH3, is that the acid? Well, does NH3 give away a hydrogen? How do you know it doesn't? Because there's no NH2, right? So now you go to the water. Is water giving away a hydrogen? Yeah, how do you know? Because there's OH. So guys, what does that make the water? An acid. So if that's an acid, what does it make NH3? The base. And then how do you figure out the conjugates? Take away a hydrogen from the acid, and that leaves you with this, which is what? The conjugate base, and the other's the conjugate acid. Does that make sense? Okay, so now guys, we got to ask another question. So which one is it? Is water an acid or is water a base? Both. And guys, there's a name for that, but the idea is this. If you add an acid to water, it acts as a base. If you add a base to water, it acts as an acid. And so water is a substance that can be both. And we call that, and you need to add this to your notes, amphoteric. Because amphoteric substances are substances that can be acids or bases. So these can act as an acid or a base depending on the other substance. And guys, water is not the only amphoteric substance. You'll see that in homework in just a few minutes. All right, so guys, now, well, I'll let you write this down, and then we need to ask and see how you're doing. You guys okay? Not yet? And guys, as we're giving people time to catch up, if you didn't yet grab your calculator, you're going to need it here in about 2 minutes. So you may as well grab it now. You okay? Okay, so guys, you tell me. Here's practice. Do we want to do more of these acid-base conjugate things, or are you feeling comfortable? Should we look at the first one and just see? Let's see how it goes. So guys, we look here, and we've got CH3. And you know what? Maybe we should do this just to mention one thing. So here we've got CH3. Does CH3 give away a hydrogen? Well, if it did, there'd be CH2. And there isn't any CH2. So now we come here. CH3COOH. Does it give away a hydrogen? Yeah, so it's right there. So guys, what that tells us then is that that's the acid. And guys, again, the minute you get the acid, you're done. Because if that's the acid, what's that make CH3 minus? The base. And then guys, to figure out the conjugates, go to the acid, cover over the hydrogen. What's left is the conjugate base, and then the other is the conjugate acid. Does that make sense? Okay, but guys, one thing we should point out, because you're going to see this in homework. Guys, look at what happens to the charge of the base. The base starts out at -1, and it goes up to 0. Notice that negative becomes 0. The reason is because this thing with the negative charge picks up a hydrogen. The hydrogen is positive, so the charge goes up by 1. Then notice the acid starts out with no charge, and its charge goes down by 1 because it loses a hydrogen. So guys, in the homework, it's going to be important for you to keep track of charge. So the thing that loses the hydrogen, its charge goes down by 1. The thing that gains the hydrogen, its charge goes up by 1. Do you want to do the other two, or are we okay? You're okay? All right. So guys, we got one more thing to do and we're done. pH. Here we go. So guys, what do we remember about pH? It's a logarithmic scale. What does that mean? Besides the fact that you hate it because your math teachers have all spoiled you because they taught you logarithms in a way that make no sense and they gave you no context, so you had no reason to understand it. So besides that, what do we know about logarithms? They go by powers of 10. Why do we like logarithms? What do they allow us to do? Count really big numbers quickly. Instead of going 1, 2, 3, 4, 5, 6, 7 up to a million, it lets us go 10, 100,000, 10,000. It lets us count really big and really small things really quickly because it doesn't move by powers of 1. So now that you remember that, guys, let's have the conversation. pH. What does the H stand for? What are we talking about? Acids. What do acids give away? Hydrogens. Guys, pH stands for something. The H is hydrogen. So what does the P stand for? It's actually not base. It's the mathematical symbol for logarithm. Because I don't know if you knew that or not, but the math symbol for logarithm is P. And so when we say pH, the H is capitalized because it's hydrogen and P means logarithm. So now we know that this is a logarithmic scale that deals with hydrogen. So specifically, what is it measuring? Well, guys, scratch it down. So guys, pH is a measure of an acid's strength, but it's focusing on the formation of hydronium ion, which you just learned about. So guys, the idea is this. Again, the Bronsted Lowry definition of an acid and base. So if you take an acid and add it to water, the acid will give away a hydrogen, and that makes hydronium. We just looked at a bunch of examples of that. And then the other thing that's left over is the conjugate base. So guys, technically then, because you can now understand this, what is pH? It's the measure of hydronium ion concentration. Again, where does hydronium ion come from? Acids reacting with water. But guys, pH is actually a measure of hydronium ion concentration. So guys, that explains the H in pH. So now we've got to talk about the logarithm. So guys, let's have this conversation. Are you guys all caught up? This is interesting. You're going to like this. So guys, this is the idea. We now understand that pH is a measure of hydrogen ion concentration. But guys, you'll notice that I've underlined the word concentration. What are our units for concentration? 2 tests ago. Molarity. So guys, when we measure the concentration of hydrogen ion, or hydronium ion, why do we use pH? Why don't we just use molarity? When we measure the strength of an acid, why don't we just say its molarity is this? Well guys, don't write this down, just follow along, because the answer is interesting, but you're going to lose it if you're writing instead of making sure you understand. But do you understand the question? If we want to know the concentration of hydronium ion, why do we use pH? Why don't we just use molarity? Well guys, the answer is this, and again, don't write, just learn. So guys, even really strong acids, like acids that I wouldn't ever use in lab because they're so dangerous, if you got it on you, you're just done. Guys, even really ridiculously strong acids have fairly small concentrations of hydronium ion. It doesn't take much to be dangerous. So guys, the trick is this. Because these concentrations are so small, it's actually a lot easier to put them in scientific notation. So what am I talking about? Well guys, if you have a molarity of 0.0001 molar, let me add units. If you have this molarity, that number's a pain in the butt to write. The problem is that's actually a pretty strong acid. So guys, we've got this problem that these molarities tend to be strong, or tend to be small, and small numbers are a pain in the butt to write, so it's a whole lot easier to just write 1 times 10 to the negative 1, 2, 3. It's a lot easier to just do that and write it in scientific notation. But guys, it doesn't stop there. It turns out that even when we put these numbers in scientific notation, they're still a pain in the butt. So yeah, this isn't great, but that's not a whole lot better. And if we had to write down numbers like this all the time, if we had to write down numbers like that all the time, eventually we would just get grumpy. So if we had to do this, guys, these numbers are no fun to write. But frankly, these are no fun to write either. So we've got a shortcut that makes it even easier than that. And that shortcut's pH. So guys, the idea is this. Let's talk about an acid with a hydronium ion concentration of 0.001 molar. That's scary stuff. You get that on you and you're going to be really unhappy really fast. But guys, again, that number's a pain to write. So what we can do is we can write it out in scientific notation as 1 times 10 to the negative third. But even that's a pain in the butt too. So guys, what we do is we just do this, and we call that pH 3. So guys, where's the 3 come from? Do you see it? It's the power. Guys, that's what pH is. So the thought goes like this. Here's the hydronium ion concentration, 0.001, pain in the butt to write. Put it in scientific notation, still a pain in the butt to write down. So what do? Instead of that, all that we do is we focus on the exponent, and the exponent is the pH. So guys, when we say that an acid has a pH of 3, what that means is its hydronium ion concentration is 1 times 10 to the negative third. So the pH is just that number right there when we write the molarity in scientific notation. Isn't it a lot easier to write down the number 3 than write down either one of those? And guys, that's why we use pH. So don't try to write this down, but let me show you how this goes on from there. So guys, here is a rather complete pH chart. So it goes from 0 to 14. Notice that stomach acid ranges from 1 to 3. The hydrochloric acid that we use in lab, actually the stuff we started with in the lab last time, which is 1 molar, is pH 0. Notice lemon juice is around 2 to 2.5. Milk, interestingly, is slightly acidic. Then guys, notice what we've got up here. We've got ammonia and then oven cleaner, which have relatively high pHs. They're basic. But guys, what does all this mean? Well, look at what you just learned. Let's take, for example, which one did I start with? Guys, let's take, for example, stomach acid. So guys, stomach acid is right here at pH 2. So guys, what does that mean that its pH is 2? Well, follow the ring. Guys, if this pH is 2, I'll bet I can zoom in on this. If the pH is 2, what that means is the hydronium ion concentration is 1 times 10 to the negative second, which is the same as 0.01 molar. So guys, what if we go to something like milk? Milk's pH is about 6. So what does that tell you the hydronium ion concentration is? 1 times 10 to the negative 6th. But guys, what does that look like if you write it out? Well, it looks like this. Do you now understand why the stronger acids have lower pHs? Guys, put that together in your head. This is in the homework. Why do the stronger acids have lower pHs? Guys, these values for pH are the exponents for the concentration in scientific notation, but it's a negative exponent. So 10 to the negative second is 0.01. 10 to the negative sixth is 0.000001. And as a result, every time the pH goes up by 1, we're adding 1 more 10th decimal, and it makes the concentration lower. So the higher the pH, the more decimal places, and the weaker the concentration. Does that make sense? Okay. So guys, what about then if we go all the way to the other end and we look at ammonia, which is pH 12? What is the hydrogen ion concentration going to be at pH 12? Well, guys, it's going to be 1 times 10 to the negative 12th. So what does that mean? Well, it means that the hydronium ion concentration is so low that the hydroxide ion concentration is greater, and that makes it a base. So guys, at pH 7, where hydrogen and hydroxide are equal, anytime you end up with such low hydronium ion concentrations that it's less concentrated than water, then hydroxide is higher, and we call it a base. Do you see the relationship? So guys, what are we going to do with this? Well, here's the trick. We now understand that there's a connection between these two things. There's a connection between hydronium ion and pH. And guys, we understand that the pH is the negative exponent of the hydronium ion concentration, but you need to see this mathematically. So check this out. There's a mathematical relationship between these two, and it goes like this. And you want to write this down. Guys, pH is equal to the negative log of hydronium ion concentration. So guys, you've got to be able to solve this equation in both directions. If I give you pH, you've got to be able to come up with hydronium ion. If I give you hydronium ion, you got to be able to come up with pH. Grab your calculators. Here we go. Guys, find your logarithm key. Not natural log, base 10 log. It probably just says log on it. You find it? Okay, now find your 10 to the x key, which is usually the second function of your log button. Got it? Okay. Guys, you want to write down these examples. Here we go. First of all, you need to understand that these brackets mean molarity. So guys, the number that will fill this bracket is the molarity. So with that said, here we go. So guys, we're going to solve this problem. Please do not write this down. Here's the problem. It says, what is the pH of a solution with a hydronium ion concentration of 1 × 10⁻⁴? What's the answer? You get it? 4. Guys, if you don't get it, get it. The hydronium ion concentration is 1 × 10⁻⁴. What's the pH? It's that. It's pH 4. Good? Now what about this? What if the hydronium ion concentration is 3.6 × 10⁻⁴? Is it still pH 4? Well, wait, there's still a 4 right there. What's the problem? That's not a 1. So you've got to be able to solve this. Guys, write this down in your notes. Ready? Write down the equation. pH is equal to the negative log of hydrogen ion concentration. Now what you're going to do is you are going to plug in the molarity, the hydronium ion concentration. You're going to plug that in for H3O+. And now you've got to solve this. So guys, if you are the owner of a TI graphing calculator, this is one of the few times that I actually like the way the TI calculator handles this stuff. You can just type this in. Remember, the negative sign is the change sign symbol thing down by the decimal. And you can literally just type in change sign log and then 3.6 × 10⁻⁴. And when you put that number in your calculator, 3.6 × 10⁻⁴, if you don't use your EE button, you're done. But guys, if you type in change sign log 3.6 EE -4 and run that through your calculator, you should get 3.4. If you don't, we've got one more example to work, and then we're going to have about 15 minutes to work on homework, and I would love to sit with you and help you become friends with your calculator. So guys, if you do not get the answer 3.4, I'll sit down with you. Frankly, what we should do is have you help each other, because you guys are way better with your calculators than I am. The calculator that I use doesn't even work in English. But we'll get you help. So guys, can we go on? Okay, so, and again, we're going on with the understanding that you may not be getting this right. And if you're not getting it right, we'll sit down one-on-one. So guys, look at what we did. You were given hydronium ion, you solved for pH. Now we're going to go the other direction. Don't write this down. What is the hydronium ion concentration of a solution that's pH 8? What's the answer? 1 × 10⁻⁻. Get it? Okay. So guys, what if it's not a whole number? What if it's 8.12? Well, now we need to solve it. Guys, write down the equation with me. Now what are we given? Hydronium ion or pH? pH, plug it in. But guys, notice what I did. I replaced hydronium ion with X. I can do that. You guys remember that in maybe 6th grade where you learned to take anything in an equation to make it a variable, replace X. It was likened to being a god. You could just change. You are now a variable. Well, guys, there you have it. Now, here's the question. How do we solve this for X? What's the first thing we do algebraically? Divide by -1. I would strongly encourage you to write this example down, because you're probably going to screw this up on the test unless you have an example to study off of. I'll just tell you now, guys, these two calculations that we're doing tend to really get people on the test. You may want to make note to yourself, study me when you're getting ready for the test. Okay, so guys, we divided by -1, and that moved the -1 over. Now what do we do to isolate x? Divide by log. But in order to divide by log, you're actually taking the inverse log. That's the second log, which is the 10 to the x key. But guys, notice you're taking the inverse log of -8.12. So in your TI graphing calculators, you can just type in second log or inverse log of negative, that's the change sign, 8.12. And guys, the answer is 7.59 times 10 to the -9th. If you're not getting that, I would also love to sit down with you individually. So guys, with all of this said and done, we still have 15 minutes. Guys, this homework is extensive. And what you're going to find is this homework is not just you regurgitating what you just wrote in your notes. Heaven forbid, you may have to think a little. I know. But guys, go through this. It is 3 pages, but it's just fill in the blanks. So, fill in the blanks. We will grade this on Tuesday. Remember, remediation starts on Tuesday. And then we'll have to do grade changes should your performance warrant it. But then guys, on Tuesday, we're going to do a day of lecture, and then we're going to go to lab on Thursday. So guys, the rest of the time is yours. Dig into the homework. If you need calculator help, I'll do my best.